All right, good morning. Welcome back to Elements of Calculus 2. So we are doing, I think, problem number 7. Nope. No, stop it. All right, problem number 7 here. All right, so let's have a look at what problem number 7 looks like. All right, using Taylor polynomials defined below, determine the first four terms of f of x equals ln of 1 plus 2x to the fourth. Okay. So what we're going to do is we're going to say, okay, let's find the one that looks like the one we have. This one has a natural log in it. Let's go with that. So we're going to say this is going to be, we are going to use the natural log one. But hey, let's go ahead and do this first. Let's set u to be 2x to the fourth power. So when I write down my Taylor series, it's ln 1 plus 2x to the fourth, 1 plus u. Let's be proper about things. Okay. There we go. 1 plus u. This is going to be u minus u squared over 2 plus u cubed over 3 minus u to the fourth over 4 plus dot, dot, dot. Okay. Now, we set u is equal to 2x to the fourth. So what we're really going to be doing here is saying that we have 2x to the fourth minus 2x to the fourth squared over 2 plus 2x to the fourth cubed over 3 plus 2x to the fourth over 4 plus dot, dot, dot. Let's go ahead and wrangle this thing around a little bit. So this is going to be 2x to the fourth minus 4x to the, because 2 squared, there's going to be 4x to the eighth over 2. Okay. Plus 2 cubed is going to be 8x to the, it looks like 4 times 3 is going to be 12 over 3. Okay, minus 2 to the fourth. Well, 2 to the fourth, 2 to the third is 8. 2 to the fourth is going to be 16. X to the 16th all over 4 plus dot, dot, dot. Okay, so fortunately, they didn't ask us to do anything more with this. They just said, go ahead and calculate this thing out. So 4 over 2 is just going to be 2x to the 8th plus 8 thirds x to the 12th minus 4x to the 16th, dot, dot, dot. That's all they wanted us to do. And again, I'm not interested in having you guys recalculate a brand new Taylor series for me. Use the one that you have. One of the things we do have to do is figure out my radius of convergence. Okay, so let's see here. Radius of convergence is -1 to 1. Okay, so we have -1 x. Good grief, get the right symbols. There we go, to 1. And it's technically u, it's not really x. So what did we really have? We have u is equal to 2x to the fourth here. Okay, so it's -1, 2x to the fourth must be less than 1. First thing to do, divide everybody by a half. Divide by 2, rather. Okay. 1 over 2. I'm going to put the negative sign out here because it's not really -1. I mean, it's negative, but we're really dealing with like an absolute value of something is less than or equal to. And then we're just going to take the fourth root. So it's going to be 1 over the fourth root of 2. I'm sure that's a delightful number. Negative less than x less than 1 over the fourth root of 2. That would be my radius of convergence for this guy right here. Okay, so as long as x is between these two numbers, which I'm sure are delightful, then this thing will work for whatever else we want to deal with it. Okay, and that's what I was looking for how do you do this problem. My favorite story about Taylor series is when I worked as an engineer and we had to figure out the length of a satellite and we were using laser propagation, and the formula for laser propagation through an atmosphere is listed in centimeters. Satellites fly, geostationary satellites fly a couple of few thousand kilometers above the Earth. So this is a really, really big number because it's in centimeters when it's really supposed to be in kilometers. And every time we would do this triangle, because I would cut this triangle in half and say, okay, I need this triangle, and we're going to figure out this side right here. And every time we did it, this hypotenuse and this height were approximately to what the computer can tell, they were the same size. So every time I would do something with it, it would just get zero. So we had a big meeting about this. We're like trying to figure out how do we do it. And the senior scientist comes in and says, hey, why don't you try a series? I was like, Bill, that's brilliant. What do you suggest? He's like, oh, no, no. I'm the scientist. I came up with a great idea. You're the engineer. You're the mathematician. You do the hard work and figure out which series is going to be best and go ahead and work out all the things. I came up with a good idea. Go make it so. Okay, thanks, Bill. I have to admit that was a really fun day at work for me. I spent the entire afternoon doing that, and that was a lot of that was probably the most fun I ever had at doing work because I was like, oh, I get to do a Taylor series. I can go ahead and make sure it actually works, and then write down the formula. I tell the computer programmers this is what you need in order to do it, and it worked out just beautifully. And that's what it is. So if you ever want to be at the star at work and you guys are having a tough time trying to figure something out numerically, just remember those words. Why don't you try a series? And then when somebody asks me, like, "Oh, that's brilliant. What kind of series do you suggest?" I'm like, "I don't know. I'm the scientist. I'm the idea person. You're the engineer. You go make it work. Okay, you took the classes where you did this, and you have all the time in the world to do it. Okay, I came up with a nice idea. So you go ahead and do the work to make it work. I'm the idea person. So try to remember that. Maybe someday in your professional career, you get to use that someday. I hope you do. But until then, good luck with the test. Good luck with studying. I have sound back now, so life is good. And take care, everybody.